Greetings everyone, I'm Giuseppe Vecchio from the University of Catania, and together with Simone Palazzo and Concetto Spampinato, I'm the author of SurfaceNet, Adversarial SVBRDF estimation from a single image. Throughout the presentation, in the bottom left corner of the slides, you will find the QR code leading to the official repository of this project. The traditional way of collecting SVBRDF maps requires expensive and complex hardware, collecting hundreds of accurately calibrated images to estimate those properties. Thanks to the success of deep learning, this problem has been increasingly posed as a learning task, exploiting the capabilities of neural networks, in particular of CNNs. All previous work have succeeded in estimating SVBRDF maps, but with some limitation. For example, with undetailed or flat normals, or with blurred maps like diffuse maps, or with specular information embedded into the diffuse map. And those methods can be grouped into three main categories: domain translation methods, inverse rendering methods, and GAN-based approach. Our method tries to overcome the limitation of the previous method. We pose the task as a domain translation task, where our network learns to map an input image to a set of SVBRDF maps. We use Altro's convolution to learn long-distance dependencies inside the image, and also a patch discriminator for two main reasons: to help the network learn to create high-frequency detail in the output maps, and to be able to unsupervisedly train our network on real images without a ground truth. The key elements of our approach are the generative approach to SVBRDF estimation, the multi-headed encoder-decoder generator based on a DeepLab v3 architecture, and the patch discriminator. The intuition behind the generative approach comes from the ability of a generative network to produce high-frequency details, and also the ability to reduce the domain shift between real and synthetic data, letting the discriminator seeing both synthetic and real data. Our network takes as input an arbitrary sized image and consists of an encoder based on ResNet 101 and a decoder consisting of 4 upscaling blocks, each receiving a skip connection with a downsampled version of the input image. Our patch discriminator consists of 6 convolutional layers and outputs a patch-level scalar prediction to be able to identify and recover fine details in the output maps. As stated before, for training we use both a reconstruction loss, a supervised loss, and an adversarial unsupervised loss. This is a picture of our framework. Now let's break it down to see how it works. The first term in our loss is the reconstruction loss. It is a supervised loss, and it consists of an L1 term plus a multiscale structural similarity loss, and it is only computed for synthetic sample, for which we have a ground truth. The second term is the adversarial loss, and it is computed both for synthetic and real sample. It helps enforcing high-frequency details and reducing the domain shift between real and synthetic images. Training and testing are carried out on the dataset presented by Deschamps et al. In 2018 for synthetic data, and on a collection of images from 3D Jungle for real data. The performance are measured in terms of RMSE between the predicted map and the ground truth map for synthetic data. Here you can see a qualitative comparison between our method and the other approaches. On the left side, we have a comparison on a synthetic image from the Deschamps dataset, and on the right side, we have the comparison on a real image. In both cases, we are using a flashlight illumination. So, in this work, we introduced SurfaceNet, an adversarial learning-based approach for SVBRDF estimation. We use the GAN for two main purposes. First of all, reconstruct high-frequency details in the output maps, And second, to allow unsupervised training on real samples. Thank you all for the attention. Don't forget to visit our GitHub pages, and if you have any questions, don't hesitate to contact us.